Okay, so we've already talked about why we form ions and all that, right? Why do we form ions?
I don't think we talked about that.
We didn't talk about why we form ions? Are you sure?
I think you're mixing us up with the week ahead class.
There's just so many classes. No, I'm like 99.9% sure, right? Who do you want to be like? You're making that face. You don't want to be like anybody? There's not cool kids on the blocks?
No, I'm too old to worry about cool kids.
Yeah, same.
Noble guesses?
You guys do not remember who you want to be like. I know I said this.
Is it noble guesses?
Yeah.
It is the noble gases, right? Everybody wants to be like the noble gases, right? That's why they're noble. You guys remember, you saw the video, you know, where they were just texting and all that crap because they were so cool? Yeah, no?
Texting, you showed us the chemical party, but not the texting one.
I showed you the chemical party. You don't remember the noble gases were just sitting there being cool?
Oh, I thought you were talking about a separate video where people were texting, and I was like, I don't remember that one.
So, no, it's the same video. It was just a segment of it. Okay, so you want to be like the noble gases. The reason why we form ions is because we want to be like the noble gases, right? Because why does sodium want to lose 1 electron? Why does it want to lose 20 electrons? And we did talk about that. We talked about electron configuration. We talked about ions. Why do you form ions?
I just know that the noble gases are the most stable, so maybe they want to be more stable.
Let's break it down. We'll break it down. I'll go back over the lecture, like pretend like you guys didn't hear it before. I know I did. I know I talked about it. Make me seem older than what I am. Okay, so in terms of sodium is right here, right? How far is it from being a noble gas?
Pretty far off.
Is it?
One protein.
Oh, no, not really.
Where is the nearest noble gas to sodium?
1 to the left. It's
Neon?
neon.
Neon. So if it loses 1 electron, won't it be just like neon?
Yes.
So sodium, being where it's at, it has the option of losing 1 electron to be like neon, or it could try to gain 1, 2, 3, 4, 5, 6, 7. What are you going to want to do? Okay, you have the option of making $500 mowing a lawn. Do you want to mow 1 lawn for $500, or do you want to mow 7 lawns for $500?
The 1 lawn.
The 1 lawn, right? Doesn't that make sense, right? So you want to find the fastest way to be like a noble gas. And so the fastest way for sodium to be like a noble gas is to lose a single electron. If it loses 1 electron, it has the same electron configuration as neon. Okay? So when we talk about the same electron configuration, what is a prefix that we often use for same? So if I say something is
ISO?
ISO, exactly. So the term, and I'm pretty sure I talked about this last time.
ISO, yeah.
ISO what?
Isoelectronic.
Isoelectronic, meaning that it's the same number of electrons. Okay, so we say sodium is sodium plus Na, or the sodium ion, is isoelectronic to neon. So we form ions and we form bonds because we want stability, right? Okay. So Jennifer, are you married?
Yes.
So why did you get married?
To be one with my husband.
Well, with your husband. It has nothing to do with stability.
To be
So
our
if
be a
your
family.
husband, if your husband was a crackhead, would you marry your husband?
No,
No. Why?
because he's unstable.
Because he's
Unstable.
unstable. Yep.
Yeah.
So you want stability. Ultimately, we all want stability. The reason why we form bonds, the reason why we form ions, is because we want to find a way of being stable. Okay? So sodium is unstable. That's the reason why if you put sodium on the table and you let it sit there, it'll actually catch on fire unless you add something covering it, like an oil that keeps it inert, right? It'll start flaming up because it starts interacting with the moisture in the atmosphere. It's so anxious to get rid of that one electron that it interacts with the moisture in the atmosphere.
Oh, funny.
Okay? So the reason why we form chemical bonds, the reason why we form ions, the reason why we form ionic bonds is because we want stability. Okay? Good so far? You got it? Simple?
Mm-hmm.
Okay.
Yeah.
So when we're talking about this, right? So we talked about like sodium, sodium plus, and all of that. So if we look at sodium alone, when it's not an ion, its electron configuration is what?
Which atom was it?
Sodium.
So that would be, I'll just do the condensed version of neon, and then it's 3s1.
Okay, so it's neon 3s1. Neon represents your core. 3s1 represents your valence electrons. So those are the electrons that you can use to either give away, or if you're in the case of fluorine, what is the short version of fluorine? The short electron configuration of fluorine.
Should I give someone else a chance?
Yeah. Give someone else a chance.
Fluorine. It would be helium as
Okay.
the core, and then let's see, 2s2, and then 2p5.
Okay. So total of 7 electrons. So it has 7 valence electrons that we have to work with. Okay. So in that case, those guys are the electrons that we can use to sit there and share. We can add to so that we can get stability. Okay. So those electrons are the ones that are going to be involved in your chemistry. They're going to be forming the bonds. They're going to be, able to interact because they're the ones on the outer shell. The stuff on that inner shell, the stuff in that core, it's kind of like it's a package up thing. It's like it's already wrapped up. You don't want to mess with it. These guys are those loose things that are kind of laying around that you can use, right? Okay, you guys kind of get that? Okay, so valence electrons are the ones that we're going to be using for interactions. Now, if you look at the noble gases, let's say we have neon here, right? Do me a favor, in the second period, count all of the electrons until you get to neon, or including neon.
5?
5?
You said Oh, sorry, I was
in
looking
the
at
second grade.
nitrogen. Yeah, 8. Sorry.
Okay, so we have 8, right? 8 electrons. So if you look at it, it has the S subshell and the P subshell. S subshell holds how many electrons, max?
2.
It holds 2 electrons. And the P subshell holds how many?
6.
6.
6.
So 2 plus 6,
8.
8. Now, I don't know, you can tell me if I'm wrong, but aren't all noble gases at the end of the P subshell?
Yeah.
Yeah? Okay, so all of the noble gases have a total of 8 in that outer shell, right? So when you get 8 in your outer shell, you're considered to be stable. So since I have 8 in my outer shell, I'm considered to be stable. So we have another way of handling that to make it a little easier than always having to write out the electron configuration. We have what we call the Lewis dot structure or the Lewis structure. So for instance, fluorine has how many electrons or valence electrons?
7.
It has 7. So what we would do is put 7 dots around fluorine. So that's letting us know that fluorine has 7 electrons to play with, if need be. Now again, fluorine wants to get to the point where it has 8. So it wants to try to form bonds where it has 8 electrons altogether. So it's going to either share, take, or give. So if I have fluorine and we have sodium, how many valence electrons does sodium have?
11. Oh, sorry, 1.
And we know that sodium, to be like a noble gas, is going to want to do what?
Give 1 electron.
Okay, so sodium is going to want to give 1 electron away. So this electron, it's going to give to fluorine, and fluorine becomes fluoride. With 8 electrons around it. And sodium has no electrons around it, so it's sort of like neon, right? So then you have your plus and your minus, and then they come together and form, in this case, sodium fluoride. Okay, so when you're drawing your Lewis dot structure, if it's forming an ion, you want to put your dots on the inside around the molecule, and you want to put your charge in outside of the brackets. Okay, so if I have sodium, not sodium, if I have fluoride, again, having 7 valence electrons, how many valence electrons does hydrogen have?
1.
Hydrogen has one valence electron. Okay, so in the case of hydrogen, since hydrogen is a non-metal and fluorine is a non-metal, what type of bond are they going to form?
A polar covalent bond.
A polar covalent bond, that is correct. So in that context, they're going to want to share that electron. So what's going to happen is that they're going to form a bond with each other. That's a huge bond. So the line represents two electrons that are being shared between the two. And if hydrogen is going to be a noble gas, which noble gas would he be? No yawning. You're not allowed to yawn. I can't yawn.
Helium.
He's going to be helium, right? Because that's the nearest noble gas. He's not going to be neon because that's way too many electrons to get, right? Okay, so it's going to be like helium. So hydrogen can only have 2 electrons, just like helium. That's the most that it can have. Now, fluorine is going to be like neon. So if you take a look, this counts as 2 electrons. So that's 2, 4, 6, 8. The fact that you have 8 electrons surrounding you make you like the noble gas. That term of having 8 electrons around me means that I've reached my octet. Okay, octet, oct, 8. Okay, so all of the chemicals, when they're bonding or when they're interacting, they want to try to reach their octet. They want to get a point where they either they're sharing electrons, so it seems like they have 8 around them, except for hydrogen. That's your exception. Or they've given away that electron, so they're like the noble gas entirely. So you have 2 ways of doing it. You can either do it or 3 ways. You can either do it by giving, taking, or sharing. Okay. So here's an example. Sodium was giving an electron away. Fluorine was taking. And then hydrogen and fluoride are sharing. Okay, you guys good? Good right there? Got it so far? Okay, so the key is, the first thing that we want to do is figure out what is the number of valence electrons that we have to work with, right? And so part of electron configuration is to try to figure that out. What's left over for us to play with, okay? So once you figure out what you have to play with, then you can sit there and draw your Lewis dot structure. Or you can just sit here and count. 1, 2, 3, 4, 5, 6, 7 for fluorine. I have 7 valence electrons. How many does oxygen have?
6.
6.
Okay, so then I would draw 6 dots around oxygen. Okay. What about carbon? How about somebody?
Okay, sorry.
That's all right. I know you get excited. Let's see. Steve.
4.
4, exactly. So then we draw 4 around that C, right? So who's going to be able to hold more bonds? Who's able to sit there and make more bonds to reach its octet? Oxygen or carbon?
Carbon?
Carbon. That's correct. Carbon. It can do 4, where oxygen only needs 2 more, right? So the most it's going to want to do is make 2 bonds if it has to. Okay? Piece of cake? Simple? Yeah, no, maybe?
Yeah.
Wait, can you repeat that again?
I said What do you want me to repeat?
Because you asked which one would
Make
reach
the most
the
bonds?
yes.
Yes. So which one would make the most bonds? Who has the ability to have more things attached to it, right? If it's going to reach its octet. How many electrons will oxygen need to get to reach its octet?
How many electrons?
That's right, because electrons are going to be what we're going to determine whether we make a bond or not, right? That determines our bonding electrons.
Okay.
So
So
how many valence electrons does oxygen have?
we had said that it had 6, right?
Okay, so it has 6 valence electrons. How many do you want to be like a noble gas? Where are the noble gases? Where are they located?
They are to the furthest right.
Okay, so they're that pink stuff in the corner? Or
Yeah.
is that pink or purple? I can't tell. Okay, so do me a favor. In the second period, count all the way to the end.
It's 4 away from neon, right?
Carbon is 4 away from neon. That's true. And oxygen is how far from neon?
2.
Okay, so that
Okay.
means it needs 2 to be like neon, right?
Okay, that makes sense.
Yeah. So who's going to be able to have more attachments to it? Oxygen or carbon?
Carbon.
To be like neon. Remember, your goal is to be like neon. Yeah, carbon, that's right. Okay, simple? Good. Let's see. So, okay, can you guys see my screen?
Yes.
Okay. Okay, so again, our valence electrons are going to be the electrons that we're going to be using to interact. Now, for simplicity cases, and also because the interactions when you're dealing with the transitional metals get very, very complicated, we often will still ignore the transitional metals, and we will only focus on those in the main groups. So when we're talking about octet, we're making reference to the S and the P orbitals, because usually that defines your outer shell, okay?
Okay.
So this is basically showing you the Lewis dot structure for each of the different main groups. So group 1, group 2, group 13, 14, 15, 16, 17, 18. Again, ignoring those transitional metals, right? So sodium is in group 1. All of those guys are going to have 1 valence electron to work with. Magnesium is in group 2. That guy has 2 valence electrons. Aluminum is in group 3. That has 13. I mean, not 13. Is in group 13. That has 3 valence electrons. As you guys already know, carbon, right, or silicon, has 4 valence electrons. Okay, you guys see that? Simple. And so, to generically write that, all we would do is say that n meaning any period we want it to be, S1, that would always represent group 1 metals. Okay? So NS1. So if I wanted to represent group 14, how would I write that?
It would be NS2 and P2.
Okay. And that's because it has 4 valence electrons, right? Pretty simple?
Yeah.
Okay. So write the electron configuration for the highest occupied energy level for group 6A or group 16. So group 16, where is group 16? Who's the top guy in group 16?
Oxygen.
Oxygen. Okay, so how would I write that, the highest energy, occupied energy level for this guy, for oxygen?
Would it be NS2 NP4?
NS2, NP4, that's correct.
Okay.
Okay. Okay, so identify the group whose electron configuration for the highest occupied level is NS2, NP4.
NS2 and P2? Is that
I'm sorry, you're right. NS2, NP2, sorry.
gotcha? I was like, wait a second.
Yes,
So
let
would
me
it
just do
be
that one, yeah.
would it be carbon or group
That's right.
14?
Group 14, that is correct.
Mm-hmm.
Yeah, I was just gonna have you do the same problem over and over again.
I was like, wait, is he tricking us?
It's been a long, long week. And I know it's only hump day.
Yes.
Okay, so we've talked about Lewis dot structures. You can do it. Excellent. Vanessa, my favorite. How you been? Have you missed me? I'm not getting the text anymore. I'm so disappointed. I'm not feeling loved. Are you there?
Maybe she went to the bathroom.
I think she's ignoring me. She broke up with me last week. That's what it was. I'm in tears. Let's see. I need a new love now since Vanessa has dumped me. I'm gonna go with Nadia. Nadia, are you there?
Yeah.
Okay, so you're gonna help me out, right? You're gonna be my new one.
Okay.
So let's see. Let's do the Lewis dot structure for arsenic.
For which one?
Arsenic? I'll spell it out. You see it?
Yeah.
Go to our P table.
Oh, let me do it.
Sorry, guys.
Are you there? Did we lose her?
I'm here. I don't know how to do it.
Oh, can you find arsenic on the periodic table? What is the symbol for arsenic?
It's AS.
AS. Okay, so what is the atomic number for arsenic?
33.
Okay, so it's right here. Thank you for helping me find it. Okay, now that we found it, so if I look at the S and the P, how many electrons are there? So this is the S, remember? And if it were me, and I had my periodic table already printed out, I would be writing that big fat S up here. Well, the little s, because it's a small case S. And then I write my P right here. So that's the S and the P. So if I'm counting all of the electrons in the same period as arsenic, so that's period 4, that is in the S and the P. How many is that? Don't get frustrated. You got this. Think about it.
How many electrons or how many?
That's right. We're talking about how many electrons. So we're talking about this. If I'm counting from here all the way to here, just counting the S and the P. We're not going to worry about the D. We're just going to skip over it.
Would it be 15?
If we're skipping over the D, we're not counting this
Oh,
part
okay.
here. This is the D.
5?
It's going to be 5. That's right. So that means that's 1, 2, 3, 4, 5. That means that arsenic, AS, is going to have 5 dots. So that's 1, 2, 3, 4, 5. Okay?
Okay.
Good job. Okay, let's see. Who else am I going to pick on now?
Wait, I have a question about the Lewis dot structure of AS.
Sure.
When it's 5, shouldn't it be 1 dot in each corner, or I guess in each side, and then only, and then a double somewhere else? Like,
So,
or why
yeah,
did you group them? I guess is my question.
I was just being lazy. So you could draw it as in 1 dot on each side.
Yeah, like that. Yeah. Or does it not matter?
It doesn't matter because electrons are mobile. And
Okay.
since they're mobile, they're going to be able to move.
Okay, so we would get it right regardless
Yeah.
where we put them, as long as there's 5 dots somewhere.
Yeah, but you're right in the sense that you don't want to have more than, like say, if you just have the single element, you don't want to have all 5 on one side.
Mm-hmm.
You know, you want to kind of distribute them. You also don't want to have 3 on one side because that's kind of weird.
Mm-hmm.
You know, so you put like 2, 1, 2, right? Or you could put 2, 1, 1, 1. That's fine.
Okay.
Yeah.
Okay, I just want to make sure I understood it well.
So it's really what you're doing is you kind of just distribute them so you can kind of get ready for bonding. So if I knew I'm going to bond with 3 things, then, you know, then I'm going to set it up so that I have, like you have it set up here. We're going to have what we call, this guy here would be a lone pair. These guys would be the 3 that would be involved in bonding.
Okay,
You know? Okay,
appreciate it. Thank you.
no problem. We'll get more into that next week.
Excited.
Okay, so you guys got that, right? Not too hard. Lewis dot structure, simple. So I need to pick on one more person to make sure that we have it. Let's see. Anybody want to volunteer?
I will.
Okay, so let's do indium.
Indium. Okay, found it. It's atomic number 49.
Okay.
And it has 3 valence electrons.
Okay.
So then the Lewis structure would be IN and then 3 dots. 1 on top, 1 on bottom, 1 on the side.
Okay. Good job.
Thanks.
Piece of cake?
Yes.
Everyone else, piece of cake?
Yes.
Yeah.
I'm calling on
Yes.
you next. So Okay, so you guys kind of got this. It's not too hard, not very difficult, right?
Mhm.
Okay. So let's talk about some trends here. Okay, so trends on the periodic table. So as you go from from left to right, the size of the atom is going to decrease. As I go from top to bottom, the size of the atom is going to increase. So let me kind of explain that to you so it makes a little more sense. Because you're probably going to say, how do you know that, right? So I said, as we go from left to right, the size of the atom is going to what?
Decrease.
It's going to decrease, okay? And then as we go from top to bottom,
Increase.
it's going to increase. Okay, so the periods, they kind of act like, have you guys seen the Russian dolls? The ones where you have this little itty bitty doll here, and then you put it inside of another little itty bitty doll, and then inside another little itty bitty doll?
Mhm.
Yeah? Okay, so the periods kind of act as little itty bitty dolls. So this is your very first little itty bitty doll. This is your second little itty bitty doll, your third, your fourth, your fifth, your sixth, your seventh, until you get the really big fat doll, right? Okay, so periods are just putting things right on top of each other, okay? So that's why it's getting bigger. And the reason why we decrease as we go from left to right is because what do you have in the center of the atom? What's in the very center?
Nucleus.
It's the nucleus. And what's housed in my nucleus?
What's in the nucleus? It's neutrons and protons.
Neutrons and protons. So what charge does it have?
Positive.
Positive, yeah.
It has an overall positive charge. So if you have positive charges, and I keep putting more positive charges, and then I have electrons that are circling, they're orbiting, they're moving around, right? So my nucleus is stable, but my electrons are circling. What's happening in that case? Here's my nucleus,
The protons
and I keep putting more protons in there, and then I just have my electrons circling. What's going to happen to my electrons?
They're gonna get closer to the nucleus.
Okay, so the more protons I have in the middle, the closer to the nucleus I get. Is that right? Simple?
Yeah.
Okay. So that's called the nuclear effect, right? Because the nucleus is causing you to get tinier, okay? So you may see a question that kind of mentioned that. Definitely in your homework, I think you guys did. Okay? So does that explain?
Okay.
Yeah.
Yeah.
Okay, so this, showing you my periodic table. This is just basically showing you what we just talked about. So you can see the general trend. Big old fat over here, gets smaller that way. Now, what you guys know about the periodic table, who's going to be the fattest atom on the block? Biggest atom.
Francium?
Francium, that is correct. Francium is going to be the biggest. Who's going to be the smallest?
Hydrogen.
Helium.
Helium. Helium's going to be the smallest. Okay? Piece of cake?
Yes, sir.
Okay.
Wait.
Somebody said wait. Or do you got it?
No, I got it.
Ooh.
Okay.
Yes.
Okay, so this is just showing you the same thing. Only thing, it just plays with the arrows differently. Okay? Okay, so refer to the atomic table and list the atomic numbers and list atomic numbers 15, 16, and 33 in the order of increasing atomic size. So atomic numbers 15, 16, and 33. So what are we talking about?
No.
We're talking about phosphorus, sulfur, and arsenic.
So we have phosphorus, sulfur, and arsenic. You know, Kristen, sorry.
Yeah.
Long day, long day. It's great. You know, I love it that it's just me and you in this class because we can go as fast as we want. You know, I love it.
Is that a criticism? Because I
No,
thought
it's a compliment, actually.
Okay.
It's not a criticism. Don't take
Yeah,
it as a criticism.
because I was
not
waiting
criticizing.
yeah, I was waiting for someone else to answer, but
Yeah, I'm not criticizing you. I'm
Okay, good.
criticizing the others who are not taking part in the activities. That's what I'm doing. Indirect.
okay.
Don't take it personal.
I'm not. It's fine. Don't worry about it.
Well, okay, good. Okay, so Kristen, since it is just me and you, you're gonna help me out with this.
You're just too good, Kristen.
I would like someone else to do it so that they can learn. You know.
Excellent. Who's gonna volunteer?
I volunteered last, so I volunteer someone else to go.
Okay. Let's see. Who haven't we heard from in a while?
Let's see. What about David?
David sounds great. Oh, we're asking. We have phosphorus, sulfur, and arsenic, and we want to list them in terms of increasing order of atomic size. So who's going to be the smallest or who's going to be the biggest?
So
The smallest is
the smallest is going to be sulfur. Then after that's phosphorus, and then it's arsenic.
Okay, so we have sulfur,
Yeah,
phosphorus,
sulfur.
and then arsenic.
Yes, sir.
Are you sure?
no.
No.
I agree with him.
I'm
You
pretty
agree
sure.
with him?
Yeah.
Okay, you're right. I'm just giving you a hard time. Good job. Okay. So just a reminder, I mean, I love Kristen. She is very animated, and Jan, she's animated. And then we occasionally get Jason to chime in every once in a while. So
Well,
now
just like
this-
Kristen, I don't want to chime in all the time either.
Yeah.
I know the feeling in some of my other classes too. Nobody ever chimes in, and it's like, well,
we
I'm the
want
only
you
one
guys
here.
to interact. And if you're not interacting, I'm going to assume that you know it. And then believe me, after you feel this first test, after you get the taste of that very first test, then you may want to change your mind and you want to start participating. The more you participate, the better you're going to do. Okay. And I know sometimes you haven't read up, you haven't got caught up on everything, right? I understand that.
Mhm.
But still, this is active learning, right? There's an opportunity to do active learning. If you're not participating, it gets really boring. I get tired of hearing my voice. And as you can tell, my voice is really hoarse right now. It's driving me crazy. So I need your help. Help me out. Make my life a little bit easier. Okay?
And also another thing is like we're not gonna judge any of you. You know, like even if I get something wrong, it's just kind of water off of a duck's back. You know, it's no big deal.
Yeah.
Well, I think it kind of depends because I remember last time I was chiming in, I think it was on the Monday meeting, but since I'm using my phone, my microphone, it's pretty bad.
Okay.
Yeah, so I legit have to put my phone like right next to my mouth.
Okay, but that's okay, you know, and we'll do our best to try to understand you. And I do understand a little bit of robot. Okay, it's a bad joke again. You guys are rough today.
You put that on your resume or what? For languages?
Yep,
A
that's
bit of
right.
robot?
Robot.
Okay, so let's see. Ionization energy. So the first ionization energy is basically the energy that it takes to remove a single electron. So that's going to be your very first ionization energy. Okay, so now I want you guys to think about this, right? So if you look on the periodic table, and the energy that it takes to remove a single electron. Now, who is it going to be harder to remove a single electron from?
Helium.
Helium, exactly. It's going to be really hard to remove a single electron from helium because of what?
Gas.
It's a noble gas, and it's already stable. Now, if you're already stable and somebody's going to take all your money, right? Are you going to let them take all your money? You're rich, but this is all your money. You're stable. Everything in your life is perfect.
I'll
You're
fight
going to
you.
let them take everything from you, right? Is that what you're going to
No.
do? You're going to fight them, right? With all
Yeah.
your energy, right? So that's
Mhm.
exactly helium. Helium is going to be like, that is not going to happen. You're going to have to put a really big fight to get this electron, you know? Okay, so
I have a question. Why is it helium specifically and not any of the other noble gases?
it's all of the noble gases.
Oh, okay. I wasn't sure about that part. Yeah.
But relative, helium is going to be, and I'll tell you why helium is going to be more so than all of the others,
Okay.
right? Helium is also, it's small, right? And you know that little statement that says you can't always judge the power by the size, right?
Yeah.
And so helium is small. It has just those two electrons. So it has a really good pull on it. Where like if you go down with radon is towards the end of it, right? The radon has all of these electrons, right? So it can't keep track of all of them all the time. So it's going to have a little bit of a weaker pull than helium does. Helium only has 2 to worry about. Radon has 96, right? And so it'll be easier to take away from radon than it would be to take away from helium. But since it's already stable, it's going to be still kind of stingy with it because he doesn't want to become unstable, okay? So their energies, the noble gases energies will be higher than those next to it. So then who would be the next strongest? Or next largest amount of energy?
Neon.
So neon, yeah, because again, it's a noble
Neon?
gas, right? Exactly. So which group would be next then? So
Would it be 17, group 17 or
17.
group 1?
So it would be group 17. Group one is anxious to get rid of it, right? Because then that means they're like a noble gas.
Oh, I see what you mean. Okay.
Okay. They're like, here.
You can
Go
have my
ahead.
money.
Exactly. Yeah, you take it. I'm too rich, you know?
Oh, man. Okay.
Okay. So do you guys see that? So these guys over here are going to have weak ionization energy. These guys over here are going to have strong or high ionization energy. Okay. So it's going to increase as we go from left to right, the ionization energy. Okay.
Okay.
Okay. So. So, and it's going to decrease as we go from top to bottom, okay? So this is just kind of showing you like sodium is going to be really anxious to get rid of that electron, where all the other guys aren't going to be willing to do that. And this shows you helium has the highest ionization energy, and then you go neon, then argon. So at the top of each of the periods, you start to see the ionization energy. So, okay. Piece of cake?
Yes.
Yeah.
Okay, so second ionization energy is the energy required to remove another electron after you removed one electron. And then a third ionization energy is to remove another electron after you remove 2 electrons already. So after it already has a +2 charge. Okay? So if you get a little question thrown in about that. This is basically showing you ionization energy. Okay, so if we're going to list these guys in the order of increasing ionization energy.
Increasing first ionization energy. As to which one has more?
That's right. That
Like,
is going to
so
have the
do-
highest
so
ionization
from-
energy.
So from highest to lowest, right?
That's correct.
Okay, sorry. I was,
I'm sorry,
can you-
not from highest to lowest, from lowest to highest. There you go.
Okay.
Yeah.
What were the atoms?
It was Be,
Boron.
N, and F. So beryllium, nitrogen, and fluorine.
Wait, and to find
You already put them in order, right?
You said beryllium is going to be the lowest. Okay. And then
Nitrogen. Fluorine.
Okay, piece of cake.
Where's Be?
So beryllium,
Oh, there it is.
Yeah.
nitrogen,
Oh.
and fluorine. Okay.
Oh,
Okay. I see.
Okay, so we've talked about chemical families. We have the alkali metals, alkali, strong reactive family, right? They have a valence electron of NS1. They don't include hydrogen, even though hydrogen hangs out with them. Okay, so these metals are very, very reactive, right? As I was talking about earlier. So if you, let's say lithium, you add lithium to water, all of a sudden you get a lot of steam and a lot of heat generated. And it'll basically make lithium hydroxide and hydrogen gas. In the case of sodium, same thing, you'll actually start getting sparks coming out of it as you add the water. I've got to modify my experiment. We actually did this experiment in my 1A class. So. And then potassium, the same thing, you'll start getting sparks. And that's because they're so anxious. They're very volatile. They're ready to react because they just want to get rid of that electron, right? It's like it's too much of a burden. They got to get rid of it. Now, on the other side, you have chlorine, bromine, and iodine. Those guys are going to be the same way. They're going to want to react pretty fast. They're also going to be pretty volatile in terms of the reactions that they form because, again, they want to get that electron as soon as they can. Okay, so the closer you are to being a noble gas, the more reactive that typical element is going to be. Okay. Okay, so these are the families. You guys should be familiar with those. You know how to find them on your periodic table.
Yes.
Okay.
Yeah.
So we have alkaline metals. And the alkaline metals are going to have what charge associated with them? If they form an ion?
Positive.
Positive what? Just positive or positive 2? Positive
Positive
2.
2.
Yeah. And then halogens. So they're one away. So if they form an ion, they're going to form
Negative 2.
negative 2. Are you sure?
Oh, wait. Sorry. Let me look at the.
1 negative.
1 negative. That's right.
Thank you.
And the what are they? catechins.
That'd be -2.
That'll be -2.
Thanks.
Okay. So this is just showing you some of the metallic characteristics, so you guys can see that the metals are they're shiny and they're malleable, and so we've talked about the noble gases. You know where they're located at. All right, group 18. And then hydrogen, it has an NS1 configuration. So, but we know that it's not an alkali metal, and it's also not a halogen. So, own special case. Okay. So this is just showing you the halogen family. Okay. And then we divide things up in terms of metals and nonmetals, right? Or I should say metals, nonmetals, and metalloids. So we know metals are going to lose electrons, and so they're going to be cations. What is a cation again?
An ion with a positive charge.
With a positive charge, that's right.
Mm-hmm.
Okay, and your metallic characteristics are going to increase from left to right, and that kind of makes sense if you look at it. Where are your nonmetals?
On the right.
Oops. Okay, they're on the right. I'm seeing. And so your metallic characteristics are going to increase from, right to left, not left to right. So these guys are your nonmetals, and you become more and more metal-like as you go to the other direction, right, towards the metals. Okay. So nonmetals, we know that nonmetals are going to be kind of dull, brittle. They're often going to be gases, things like that. They're going to be horrible at conducting electricity. So they're great, or conducting heat. So they're great insulators, typically. Metalloids are going to have characteristics of both metals and nonmetals. Okay. These are the properties of your metals. So you guys can see over here. These are the properties of your nonmetals. Okay, just a quick, very quick table. Okay, this is just showing you the location of them. And then the very last slide, these are the metallic characteristics. Questions, concerns, Cash. Okay, that's it. That's it for chapter 11. Are you guys good?
Yeah.
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 Okay, so your exam will cover everything in chapter 11, all the way up to chapter 11. So it'll be 2, 3, 5, and 11.